All right, so in this video, we are going to derive the D4d character table. And so in deriving these character tables, it's helpful a lot of times for visualization, is explaining it in the videos, to use an example molecule. And so sulfur, which is S8, and has this crown structure, is what they call it, is of D4d point group, and it has that symmetry. And so the principal rotation axis, or the highest order Cn, is actually a C4, and so it's a 90 degrees rotation. So this atom that's in the top position gets spun over to here when it goes 90 degrees, and then this goes to here, this goes there like that, and then the bottom ones, you can see they're also 90 degrees apart from one another, so they all rotate to one another. So that's sort of where this D4 comes from. And then, of course, we're going to have perpendicular C2s. We're always going to have, remember, in any DN point group, a DN point group is a DND point group, we're always going to have N perpendicular C2s. So perpendicular is the principal rotation axis. In this case, we're D4D, so N equals 4. We're going to have 4 perpendicular C2s. And here they are. You can see it flips the molecule on itself, and sort of takes this to here, this to here. We're talking about this axis here. Okay, so they're a little hard to visualize, but they cut in between the bonds here. And so we have 4 of them. So first thing we need to do here when deriving the character table is come up with all the different symmetry operations, and then once we do that, we'll group the symmetry operations into classes. So we have an identity. Obviously, we always have an identity. We have the C4 that we talked about. We have these 4 C2s, and I'm going to put a prime next to them to tell us that they're perpendicular to one another. Kind of already drawing it like this, I already grouped them into class. They're going to be one class together. They're all very similar type of rotation, these perpendicular C2s. But then we can generate some other operations from this C4. We can have a C4 twice. That's going to be equal to a C2. That's a 180 degree rotation. So it's taking this atom and taking it to that atom, this atom taking it to that atom, and doing clockwise rotation. And then we'll also have C4 3 times. Okay. And in previous character table derivations that I've done before, we've had this pattern where the C2 is in a separate class. So if we're to highlight classes here, identity is always in its own class. These C2 primes, as I talked about, they're similar. They're going to go in the same class. And the C4 and the C4-3, those go in their own class. We're going to call 2C4. And this C2 is a little bit different because it's doing a 180 degree rotation, right? C4-3 is doing a 270 degree rotation, but if you define things the opposite way, that's just a 90 degree rotation in the opposite direction. So C4 and C4-3 are similar in what they do, so that's why they go in the same class. So we can start sort of grouping things into classes here. And then there's actually quite there's mirror planes, and these are sigma Ds. And why are they sigma Ds? Well, you can tell from the name they have to be sigma Ds. There's 4 of them, so there's 4 sigma Ds. All those do similar things, so they're going to be the same class. Now, why are they sigma Ds from a technical standpoint? It's because these mirror planes, they bisect two perpendicular C2s, each of them do. So the mirror plane lies around one of these mirror planes, right? It lies along this plane. It's going through the atoms, not going through the bonds, okay? If it went through the bonds and it was coincident with the C2s, we call them sigma Vs. But there's no DNV point groups. Instead, we have the DND point groups like this one, D4d. And so those are the main operations, but there's one other types that we're missing, which are the improper rotation axis. And in this case, this is actually going to be an S8. We actually have an S8 that's coincident with the C4. A little tricky to see, but basically the way that this works is that, remember what an improper rotation axis is. So an S8, and I should be using hat notation here when I'm talking about an operation, but when I'm grouping them into classes, then I drop that hat notation. Classes don't use the hat notation, operations do. But when we're talking about, an S8 operation, what is that? That's a C8 followed by a sigma H. Now this molecule doesn't have a sigma H. That's a horizontal mirror plane. So it's horizontal to this principal rotation axis, the C4. That doesn't exist because if we draw a mirror plane, horizontal to this, a little hard to draw here, but let's say something like that, that would take this atom and go to the bottom, right? And there's nothing there. However, if we do an S8, well, now we're not doing a 90-degree rotation, we're doing a 45-degree rotation. When we do a 45-degree rotation, what that does is, for example, it takes this top atom and rotates it to a point above, to the space above where this other sulfur atom is. So then when it gets flipped with the mirror plane, it's going to come down right there. And same thing with this atom. This atom's is gonna go. Let's use a different color. This atom's going to be rotated down because it started below, but then it's going to flip up with the mirror plane and go into that atom where it exists. So that's how you can visualize this improper rotation axis that exists, this S8. And from that, then we can start thinking about, okay, we have an S8. Well, if we have an S8, just like we could do a C4, when we had a C4, we could do C4 twice. We can do an S8 twice. Well, what happens when we do an S8 twice? Well, that's just a C8 twice, and it followed by sigma H twice. Well, sigma H twice is the same as identity, flip up, flip down, so that drops out. You end up with just a sigma C8 twice, which is just equal to 45-degree rotation twice, which is equal to 90-degree rotations, that's equal to C4. So we already have C4, that's not a unique operation. What about S8 3 times? That is going to be unique. That's going to be equal to a C8 3 times, followed by a sigma H 3 times, which is just equal to sigma H, because these odd number of flips. So you flip from bottom to top, for example, then top back to bottom, then bottom to top. That's the same as just doing from bottom to top, 1 sigma H. That's going to be unique, and you can see this exists, right? Because it'd be like taking this, rotating it all the way over here to this point, three spaces, right? 1, 2, 3, 135 degrees, and then flipping using that sigma H down into there. So it traces onto itself. There's a sulfur atom there. So this is a unique operation that exists. And so you can keep going through this. Basically, any of the even S8s aren't going to be unique because they're going to transform as a C4 derivative. So like an S8-4, that ends up, I think you can show it pretty easily, is equal to a C2. But an S8-5, that's going to be unique, right? So that's going to be equal to a C8-5 followed by a sigma H. That's unique. And then we would also have an S8-6 is not going to be unique. That's just going to be equal to a C4 3 times. But we would have an S8 7 times. That would be a C8 7 times followed by sigma H. And so hopefully what you can see is that an S8 7 times, and by the time we get to S8 8 times, we're back to identity. That's a 360-degree rotation followed by 8 flips, which doesn't do anything, that's identity. But we can see is that, hopefully we can see is that S8 7 times and an S8 1 time are very similar. All we did was in one case, we flipped over 45 degrees. In the other case, we flipped all the way around almost 360 degrees. We went up to here. And that's very analogous to just doing 45 degrees counterclockwise versus clockwise, right? And so those are similar depending on how you define your direction. So those are going to be in the same class. So we'll group those in a class called 2S8. And then very similar, in an analogous way, the S8-3 and the S8 5 times, those are both 135-degree rotations in different directions. So an S8 3 times, so let's see, S8 3 times and S8 5 times, those are going to go in the same class. We're going to call those 2S8-3. because there's two operations in there, an S8 5 times and an S8 3 times. Just like in the 2S8, there's S8 7 and an S8 1 time. But those are analogous too, right, to each other, because you could go over to here, or that's S8 3 times, or you could go all the way over to there. But for that first one that I drew, that first red line, that's just going 3 spots over. If I go 3 spots over in the other direction, I get to the same point as going to 5 spots over in clockwise direction. So those are analogous. So at this point, we've basically figured out what our symmetry operations are, and we've grouped them into classes. And you can see we have 1 plus 1 plus 4 plus 4, that's 10, plus 2 plus 2 plus 2. We have 16 symmetry operations, and we've been able to group them into 7 different classes, right? So we have 1, 2, 3, 4, 5, 6, 7. And so that is the first step to figuring out how to derive a character table. You got to figure out all the symmetry operations always, and then you have to group them into classes. And so from there, we'll continue and start building out our character table. This is most of the visualization is in this step here.